Friends, welcome to the online course titled Risk and Reliability of Offshore Structures. We are talking about the first module lectures, where we are discussing introduction to reliability and some introduction to plausible reasoning and probability theories. Today we are going to discuss about lecture 9, which we will focus on probability distribution. In the last lectures, we have established a connectivity between reliability and safety. We have also established a connectivity between reliability and probability of failure, where failure is a negative note on a given performance of a system, whereas reliability looks at the positive side of efficiency of performance of a given system under the specified load and period of time. We have also said how reliability and risk can be connected and what is the necessity of doing a risk assessment and how reliability is more generic in nature compared to risk assessment, because risk assessments lead to regulations of formations of rules, whereas reliability is more or less a general form of assessing safety. However, we also said reliability can be established only in probabilistic terms. Therefore, tools of probability are very useful in establishing reliability of any given structural system. Therefore, we discussed about rules of probability, which are very useful in understanding reliability theory in the next series of lectures. However, probability seems to be a more mathematical way of expressing confidence of any event. Therefore, we took the help of physical understanding of this using what we call plausible reasoning. Plausible reasoning is nothing but simple rules of thinking of human brain, and we said that a given knowledge of a specific event will be able to establish more level of confidence of occurrence of that event. Therefore, we have seen if there are two events, let us say A and B, which are mutually exclusive and exhaustive, we can connect them in many ways and we will be able to establish the probability of occurrence of event A, provided we have the knowledge of probability of occurrence of event B or any other additional knowledge on event B and A, what we said as plausible reasoning. However, in these discussions we had so far have discrete set of propositions. So, we have been discussing discrete set of propositions, though we all understand that proposition set or establishing a set of proposition for a given system itself is highly complicated, but still we have been talking about discrete set. However, in offshore structures there are events which are interconnected and they cannot be discrete and they remain continuous in both space and time. Therefore, the events that challenge safety or, to be very specific, which leads to reliability analysis are continuous both in space and time. So, we have been discussing about discrete set of propositions, but now we have events or set of propositions which are now continuous in both space and time. Then how do we handle them? Therefore, the reliability analysis when applied to offshore structures now gets a new dimension. Let us say let F is a continuous variable of interest then the propositions of f can follow like this. F can lie either less than a variable which is defined as q, or f can be greater than q. Interestingly, when we have got a variable q which is actually continuous in both space and time, we are dividing this f in terms of q at two discrete set of values. So, therefore, whatever rules of plausible reasoning and whatever rules of probability and combination of events which we have studied so far can be directly applicable, because now we are talking about discrete and they are mutually exclusive and exhaustive. Therefore, all rules what we studied so far can be directly applied for reliability studies, even though the events or set of propositions will remain continuous both in space and time. Now, interestingly, given some information on event y, let us say given some information on event y, one can express a function like this, which can be equal to probability of given event y. Now, one can easily see from this equation 2 that the function will now remain monotonically increasing function of q. Equation 2 represents monotonically increasing function of q. Now, in addition to defining the function, one is also interested to know the probability that value of f lies within a specified interval, because we would like to know, because we are defining function in terms of q and q has got an interval. So, we would like to know what is the probability that my function f will lie within a specific interval. So, now this can be specified as, to express probability of f to lie within a specified interval. We can write that a can be expressed as less than a, let b be expressed as less than b, and hence w can be expressed as an interval of a less than f less than b. To be very specific, we can even say this way. Now, for two events a and b which are mutually exclusive to occur, we can use the sum rule. So, now using the sum rule for two events a and b which are mutually exclusive, one can use the sum rule, and we can write that as probability of a given y can be said as probability of a given y plus probability of w given y, because w is an interval between a and b, and a is indication of and b is indication of this. So, let me call this equation number 4. But by definition we have probability of b given y as g of b because one can easily say let G of q be probability of f given y. So, one can say that probability of b given y be G b and probability of a given y is G a. Then equation 4 can be rewritten as probability of a less than f less than b given y is nothing but probability of w given y, which is as good as G of a plus G of b. Now, since G is a continuous and a differentiable function, we can also write as follows: probability of a less than f less than b given y can be said as integral of, because it is differentiable function between the limits a and b, because we are all the time trying to express the interval between a and b where the probability of f is sure to lie, G of f df. Only equation number 6. Where G of f is nothing but greater than or equal to 0. Therefore, G of f is nothing but the derivative of G, which is generally called the probability distribution function. Can also be called as probability density function for f given y. The integral of G of f is called cumulative distribution function for f. The above equation, that is equation 6, leads to ambiguity when G of q is discontinuous at any point q naught. So, equation 6 will lead to ambiguity when the function G of q is discontinuous at any specific point, let us say q naught. Therefore, it is important for us to note that the function approaches the limit in such a manner that the density function develops a sharper and sharper peak, leading to the limit delta function, what we call as the function approaches sharper and sharper peak it will lead to a delta function. Which is given by P naught delta of q minus q naught, where q is actually the function and q naught is the point where the function becomes discontinuous. So, this signifies a discrete hypothesis. We call this signifies a discrete hypothesis, which we call H naught. Therefore, the enclosing area or let us say the limiting area will be equal to the probability P naught of that hypothesis. So, therefore, one is now interested to test the hypothesis. So, now let us talk about testing of hypothesis. Let A represent a proposition. Let us say for example, let A represent a proposition that fraction of bad or failure members in the range, proposition that fraction of failure members in the range f and f plus d. In such case, a prior PDF can be calculated, which will be given by probability of A given x, because talking about the event A given x is nothing but d of f given x dx. So, this gives equation 7 gives the probability that the fraction of failure elements in the range f and f plus df. So, let us say we are conducting experiments or inspection, let D represent the result of experiments. In our case, let us say we are conducting site inspection. We may conduct some non-destructive tests, we may conduct some destructive tests. Let us say we are conducting series of experiments. Let D represent the results of these experiments conducted to identify the failure or to identify which is a failed member, which is a safe member. So, we say the good members or safe members are G and the bad members or failed members, let us say B. Then the posterior PDF for the function f can be calculated. Please note, in the beginning we are a prior PDF, we have no knowledge about the test results which we are going to conduct to identify amongst the given set of structures which members have failed, which members are good. So, we have a prior PDF with us. After conducting experiments or inspection or NDTs, we have results. Now, we have classified amongst the given set of structures, set of members, G are those set of members which are very good and G or B are those which have failed. Therefore, I am now interested in finding out the posterior PDF of the function f. So, the posterior PDF of the function f is given by P of A dx, which is P of A given x. We already have this information with us. P of D given Ax by P of D given x, where D is the test results, which is as good as G of f given dx df. Let me call this equation 8. So, this is the equation representing the prior PDF before we had some knowledge about test results conducted on the site. Once we conduct the results experiments, we have the results, we identified some as good and some as failed. Therefore, we are looking at the posterior information of this and we call that equation as 8, which is going to now give me. So, one can very easily see here, this is P A given x, whereas this is P of A given dx, because D is now the test results conducted on different set of structures to identify the failed systems. Hence, G of f given dx is G of A given x P of D given Ax by P D given x, where we have used the rules of probability which I discussed earlier. We call equation number 9. In equation number 9, you can see here the denominator is actually a normalizing constant which can be computed directly. Following the condition, we can use to determine the denominator. We can also determine the denominator using the following condition: P of 0 less than f less than 1 given dx, because I am checking out the probability either it is failed or it is safe. So, between 0 and 1, which can be said as integral of 0 to 1 g of f given dx df, which obviously will be equal to 1. So, in this equation 10, since f is the only varying parameter and P of D given Ax, P of D given Ax is a continuous function of f, P of D given Ax can be replaced easily with the function which I am going to write now. So, let us replace P of D given Ax with a function. So, replacing P of D given Ax as P of D given h of x. So, therefore, at any random pick, if f is a fraction of the bad or the failed elements, then probability for picking a bad or a failed element at each trial would be f, while that of getting the better element of G will be 1 minus f. That is very interesting now. Let us say in every trial or every inspection or every test you have conducted on different kind of members at a random manner, if f is the probability that you will pick up or you will identify bad or let us say failed elements are identified, then the probability of identifying the non-failed or better elements, safe elements, would be 1 minus f. So, one can easily understand now we are trying to relate slowly the failure and reliability. So, this can also be seen as a result of inspection of set of offshore structures, and you are looking for a case where the failure of offshore structures after a specific period of service life. Let us say probability of each trial are actually the hypothesis. Which is hidden in X, because we do not know the data X, which is logically independent. On the other hand, if you got 10 structural systems in a given location on which you are going to conduct inspection or experiments, please understand the failure identified in one set of structures does not influence the failure of the members on other set of structures, because they are far apart. So, the hypothesis is very clear, which is hidden in X, says that they are logically independent. So, given F, the following statement is valid, because you already find the probability of identifying the failure. So, given F, we can say, we can state probability of D given H of x, which is the hypothesis which has replaced D of x. D is the test results, nothing but f of n 1 minus f of n minus n, where n is a total set of offshore structures what we inspected and n is that has failed. So, it is important to note that the factors do not appear as we have knowledge of the order in which the results appear. So, posterior PDF now can be rewritten as probability of D given H of x is f n 1 minus f raised to the power of n minus n g f given x divided by f 0 f n 1 minus f n g of f of x df, equation number 12. For example, in a multiple hypothesis tests, prior PDF can be given by a simple case. Let us take a multiple hypothesis. Prior PDF is given as an example as g of f of x, let us say 10 by 11 of 10 power minus 6 of delta f minus 1 by 6 plus 1 by 11 of 1 minus 10 power minus 6 of delta of f minus 1 by 3 plus 10 power minus 6 delta of f minus 99 by 100. This is a case where the cumulative function of g of f is discontinuous. I am having discrete values. 3 delta functions, what you see here 1, 2 and 3. The 3 delta functions what you see in this equation corresponds to 3 different hypotheses, namely A, B and C. So, for a multiple hypothesis test, as an example, a prior PDF can be given by this equation as shown in the blackboard now. Now, let us consider inspection of an offshore platform for damage assessment. So, we believe that there is no prior knowledge about the damage, except that there could be a damage since the platform is very old or age of the platform is relatively high. In such cases, one will be curious or interested to know what is the prior probability that should be assigned to this structure. One way to answer this question is assume this as a constant. So, do not connect the type of platform, its location, age, operational conditions etc., before you assign the prior probability of failure. So, prior information if not known will lead to assigning a constant probability as prior information. So, do not use any data which can be available based on which you are not sure whether the failure has occurred or not. So, then in order to normalize it correctly, one must consider the following, because since I have not considered any information available to me, I have taken this as a constant. So, I need to normalize this. Okay. So, let us consider the following. Say G f given x, let us say is 1, 0 less than f less than, equation number 30. Now, knowing the prior information about the failure which was assumed to be constant, then the following statement is valid. So, for a constant prior information, we can state as follows: probability of D is representing inspection and this is based on hypothesis, that is why it is denominator is replaced, which was normalizing the hypothesis. If you look at the equation earlier, which now becomes Fn 1 minus f n minus n, which we already wrote also. Suppose I have a prior knowledge about the failure status of offshore structure, I want to use it. So, now this equation 14 can be modified. If prior information or knowledge is available, then equation 14 can be modified. Probability of D given h of x, which is n plus factorial by n factorial n minus n factorial, because in an inspector platform earlier of capital N you already saw that small n were failing. So, you have a prior information. Multiply this factor to your information. Equation number 15. So, if you compare equation 14 and 15, 14 did not have any prior information, there was a constant. 15 had a prior information because you tested n platforms earlier, out of which small n were the failures. Therefore, you modified the equation with the known information. The right hand side of this equation has a peak within 0, okay. The RHS of this equation has a peak within 0 less than f less than 1. Located, this can be located by differentiating, which can be located by differentiation, that is f dash n. Now, one is not only interested in knowing the point, we also know what is the sharpness of the peak. So, one can expand the function in a power series as given below. So, to know the sharpness of the peak, one can expand the function as power series, which is given by, let us say, L of f, which I call as L of f hat, which can be f minus f hat divided, where sigma square is 1 minus f by, I call this as equation number 60. Having said this, I will now modify the equation. Probability of f given dx is exponential L of f hat, L of f, which is approximately k times of exponential of f minus f hat square by 2 sigma squares. Equation number 70. It can be easily seen from the equation that it follows a standard Gaussian or normal distribution. It looks like follows a standard Gaussian or a normal distribution. We can also extend this discussion for simple and compound hypothesis, which we will discuss in the next lecture and touch upon introduction to random variables. So, in this lecture we discussed how to handle continuous variables with the knowledge and information we had of handling discrete set of propositions. We also said how to apply test hypothesis if it is single or multiple propositions, and how the failure or probability of failure can be related to reliability indirectly using the studies what we so far discussed. Thank you.